and welcome to a presentation on a simple hydraulic circuit where we're going to look at how pressures are distributed in this circuit. So what we'll look at is we'll look at a circuit that contains a pump driving a cylinder through a directional control valve. There are a number of not complicated relationships, but the interconnection between the relationships is a little bit tricky, so it's worth looking at it and learning it in detail, especially since this is a very common circuit. We're going to see how the load affects the pressure distribution in the circuit. We will look and see what happens to the pressure distributions in that circuit as we operate at different velocities, different cylinder velocities. And then we'll look and see how the pressure distribution in that circuit goes when we change the force on the cylinder. This is a circuit. So what we have here is we have a single rod cylinder. So there's only a rod on one side, but it's in a double acting application. And what that means is that we can drive the cylinder either to the right in extension or to the left in retraction. We'll first consider this case of extension. And actually what I've shown here, this is the DCV here, is I've shown only one envelope for this, and this is the extension envelope. We will look at a simple case to start out with. It's just a steady state case, so we will not be looking at dynamics. We'll simply be moving this load, which is a steady force, at a specified speed. We could, after doing this, develop a dynamic model for this, but that's not the topic of this presentation here. Though I've already said this, but it's a case of moving a mass against a steady counterforce, which I call F load here, at a steady speed. That's a very common application. In fact, I've shown this load here really as a result of friction, of viscous friction. So if you were moving a mass at a steady velocity in a application that had viscous friction, you would get a steady force in return. But it also covers the case if we turn the cylinder vertically and we're simply lifting a weight. That is the same application where you're lifting the weight up at a steady speed. So we have certain assumptions. We're going to do a really simple case to start out with, and then perhaps in later videos we can we can get rid of these assumptions one by one to see what effect that has on the system. So we're going to at first ignore the pressure drops in these lines from the tank to the pump, from the pump to the DCV, from the DCV to the cylinder, and then back out from the cylinder to the DCV, and from the DCV back to the tank. So we're just going to say that there's no pressure drop there. The case that we're going to cover is the case of moving at a constant force at a constant speed. And then we're going to assume no leakage. So there's no leakage in the DCV from the P port to the T port. And then we're going to assume that there's no leakage around the piston from the cap side to the rod side. Other assumptions. We'll start out by assuming that the relationship between flow rate and pressure drop across the DCV is linear. Okay, so we're using a sort of Ohm's law for fluids, where we have our flow on one side, we have a resistance, that's the valve resistance, times a pressure drop. So this is like Ohm's law really for fluids, where this would be I if it were electrical. We'd have a resistance, and then we'd have a change in voltage on the right hand side. This is not actually the case. The relationship between Q and delta P is not linear, but there are, even with a nonlinear relationship, you have ways of linearizing it. So we'll do the linear relationships at first, and then we'll perhaps look later, not in this video, but later at how this would be done with nonlinear relationships. You'll get more accurate results if you use the actual nonlinear relationship than if you linearize it, but there are advantages to linearizing it too. More assumptions. We'll assume that the characteristics, the flow pressure drop characteristics of the P to A port are the same as the flow characteristics of the B to T port. And that's normally the case. This has to do with the internal geometry of the ports in the DCV, and usually they're made to be the same. So if you have the same pressure drop across each of these orifices, you'll have the same flow rate through them. Now we have some basic relationships that impinge here, apply here. If we know V, so if that's specified, the velocity of the load, then we can calculate the flow rate into the cylinder and the flow rate out of the cylinder. Those are just going to be the swept volume times the velocity. Now, if we know, so we know the velocity, we know the flow rate in, we know the flow rate out, we will have manufacturer's data for this valve that will tell us what pressure drop here you need to have that flow rate into the cylinder, and what pressure drop you need here to have the flow rate across here that you have out of the cylinder. And I've already said that, so we'll continue on. Now, in this case here, if we're specifying the load and the velocity, we want to move a certain load at a certain velocity, we have to let PP float. And we'll talk more about this later, but we're going to, for this analysis here, we're actually going to let PP float. We have to let it float if we're going to specify both of these. Now, how are the calculations going to go? Well, like I said, we're given the velocity, and with the velocity we can actually calculate flow rate. We have two different flow rates actually, because the flow rate is equal to the area times the velocity, and we have two different areas. We have an area on the cap side and we have an area on the rod side. So the flow rate across the PA orifice in the DCV is equal to the area of the cap times the velocity of the load. And on the other side, the flow rate out of the cylinder and across the B to T port in the DCV is going to be equal to the rod area times the specified velocity. Now, since they're not the same, that means that the flow rates are not the same, because they are both multiplied by the same velocity, and that means that the delta P's across the DCV are not going to be the same either. In fact, since the flow rate here on the inlet side is greater than because of the greater cap area, the flow rate here is going to be greater than the flow rate here, and therefore the pressure drop from PP down to PA is going to be greater than the pressure drop from PB down to PT. But then we have another important relationship here that we need to consider, namely the load force. We specified a constant load force also, and that load force is going to be it's related to these pressures. So we get the pressures on both sides of the cylinders and use the respective areas, and we can calculate what F load is going to be. So F load depends upon the flow rate, or not the flow rate, the pressure drop across the piston. But let's not forget at the same time, we have another relationship that we shouldn't forget, that the flow rate across the orifice is related to the pressure drop on both sides. PT, assuming we have an atmospheric tank, is 0, and therefore on the right hand side we only have PB appearing, not PT. Let's go through these interconnections, I guess you would say. The flow rates are related to the velocity, which is specified, but the delta P's across the DCV are related to the flow rate. So that means that the delta P's are related to the velocity also. And then the delta P across the piston determines F load for a steady velocity, because at a steady velocity the piston force is equal to the resistive force that it feels at the end of the, where the mass is. So our strategy for solution is we get the Q's from the given V, the inlet Q and the outlet Q. And then we work our way backwards. We start where we have zero pressure, and we know the pressure drop across here since we know the flow rate through that orifice, so we can find PB. And then we bring the load in, and knowing the load, we can actually use our relationship to get PA to support that load. But knowing PA and knowing the flow rate into here, we can calculate what PP would be. So we'll have a certain pressure drop across here because of that flow, but we need a certain pressure here, so we can calculate how much further up above PA PP will be for that given flow rate. So you start backwards and work your way from zero pressure or atmospheric pressure to your highest pressure in your system. Now let's look at some observations about this scenario here. In order to sustain a higher resistive load here, if you have a higher resistive load against which you have to push at a steady velocity, that means that you have to have a larger pressure drop across the piston. But the problem with this is that PA actually comes from PP. It's a reduction in pressure from the pump pressure down to the pressure that's on the other side of that orifice. And then PB is actually above PT by a certain amount too. So to sustain this load, I need to have a high PA and I need to have a high PB. But the PA is related to the flow rate. So we're seeing a complication in the relationship between F load and V. So for PA to remain high and for PB to remain low, which you need for a high piston force, you need to have low flow rates so that PP does not drop too much to PA and PB does not have to be much above PT. So if we want to sustain a high force, we need to have a low flow rate so that we can keep this pressure high and this pressure low. But to have a low flow rate, we have to have a low velocity. I've just said this here, so I'll continue on. So you have a trade-off between if you have a high load, you're going to have to move at a lower velocity. And if we set F load higher and higher, so we need a greater pressure here and a lower pressure here, eventually you'll set F load so high that you can't have any pressure drop here. You can't have a pressure drop from PP to PA, nor can you have a pressure drop from PB to PT. So basically, you set the load up high enough, and it makes it so that the load stalls, and at that point you have zero flow rate. And with zero flow rate, you have no pressure drop across the DCV. The DCV is still open. So what that means is that PA rises to PP and PB drops to PT, which is zero. So I've just said this. We'll continue on. So at the stall force, so that would be where F load has risen high enough that you can't move the load. then our relationship, and I really should have put PP here because PA is equal to PP. So we have our highest pressure in our system pushing against the cap side of the piston. We don't have minus PB times A rod because PB is now equal to PT, which is 0. So we have our full system pressure acting on the cap side of our cylinder. Let's continue on with this. Now let's focus on V. So we have a certain F load, and we're going to increase V. So we increase V higher and higher, and of course if we increase V higher and higher, the flow rates have to increase also. And then with higher flow rates, that means that the pressure drops across the DCV have to be greater too. So PA gets lower with a higher flow rate. And so if we keep increasing this V, the load that we'll be able to carry with that V gets to be lower and lower and lower. And eventually the pressure drop across here is so high, and the pressure rise, or actually it's pressure drop, but if we look at this side, the pressure here gets to be so high that we have no load on the cylinder anymore. So we can't support an external load. But at that point, the velocity is as fast as it can be. So if we reduce this load, then the velocity that we can sustain is higher. So you have a trade-off between load and velocity. So that we can say that for a given V and F load, so if we're going to move a steady load at a steady velocity, to do that, we're going to have to control PP. We let PP float before, but now we've seen through our calculations that we determine PP based upon F load and V. But this is not normally how you apply or operate in this scenario. If you're moving at a steady load at a pre-specified or specified velocity through an open DCV, the way to do that, if you want to control it, is to control PP. But it's not normally how it's done. Usually PP is not controlled, it's not modulated. What happens is PP is set by the pressure relief valve in the circuit, which is not shown here for simplicity purposes, but there's a branch that comes off of this discharge line of the pump that goes back to tank, and it has a pressure relief valve in it, and the setting on that pressure relief valve is the pressure setting, the maximum pressure setting in the circuit. And what we do in that case, if we want to move a specified load at a certain speed, is we actually replace the DCV with what's called a servo valve. So we don't have a fixed orifice here. We can change the orifice, and therefore we can change the resistance, and therefore the pressure drop across the servo valve. So what we're doing, and I've said this already, is we're controlling these resistances on the inlet port and on the outlet port so that we can deliver the correct pressure drop here for the load moving at the given speed. And this is the end of this presentation on these pressure distributions in DCV for the special case, but the very common case of moving a steady load at a specified speed. Thank you for watching.